Hi there, so this is the notes for restricted values. So we started off with a warm up here, or just the problem asks us to evaluate. So remember, we're plugging in. So we're plugging in -2. We see that plugging in everywhere where there would be an x in the problem. And what we saw when we plugged in -2 was that we got 15 over 0. Remember, every time we divide by 0, it's going to be undefined, right? So we find that when we plug in -2, we get an undefined answer. And when we plug in 3, we get an undefined answer. So we had a kind of a weird moment like, whoa, that's weird. Why did that happen? And so we're going to think a little bit more about what made that happen. So when we look for the factored form, so the next step it says is to rewrite the factor f of x in factored form. We took this equation here and wrote it into its factored pieces. So you can see this section here factored into x minus 3 and 2x plus 1. And then this section here factored into this one there. So you can see when we write the restricted values that x is not allowed to be 3 and it's not allowed to be 2, right? Not allowed to be 3 and not allowed to be 2. And what we see is that those restricted values are what made it undefined. And interestingly, if we look at the graph, we can see that the -3, when we go to where x actually is -3, 1, 2, 3, over here, we can see that we have that hole there, right? So that hole is how the restricted value shows up. And then this -2, right, from x plus 2, be turned into this vertical asymptote. So we're going to see how that plays out today in a little bit of our exploration. But a restricted value is an x value that has no y value, right? So it's an x like 3 or like -2 where the function does not exist. So we see that in particular with holes and with vertical asymptotes. So we're going to save our big idea for right now, but our goal is to go down here. We're going to go ahead and fill in each of these boxes here. So I'll do the first one with you. Go ahead and delete this. So we have this graph here, and they tell us what the equation is, and our job is to do the factored form. So we want to factor this into whatever we can. I know this is the difference of squares, so I know this is x plus 6, x minus 6, and I can see here I can take out 2x, and that leaves me with x plus 6. I see here that x is not allowed to be 0 from this, and it's not allowed to be -6 from that. So I know those are going to be in my two places where there are either holes or vertical asymptotes. So looking at my graph, I can see them there. So it says write the factor that cancels. So looking here, I'm going to see, okay, x plus 6 and x plus 6 cancels. So I'm going to write that down. We're going to solve for x. We're setting equal to 0. So subtracting 6, x equals -6. And our job here is to look at the graph where x equals -6. Where does x equal -6? Over here, I can see x equals -6, and there's a hole right there. So I can see that this one, means at this point, there is a hole. So take a moment to write out that there's a hole at -6. The next section says, write the factor from the denominator that doesn't cancel, right? So looking back from the denominator only, what part doesn't cancel? 2x. So we would say 2x doesn't cancel, equal to 0. We're going to divide by 2. We get x equals 0. So looking back at the graph, where x equals 0, we can see that we have that vertical asymptote. Right? So we can write here, vertical asymptote. You can abbreviate VA if that's helpful to you. I'll just write it out this one time so we know it. But we have our vertical asymptote at x equals 0. So we can see our two discontinuities, right? These two restricted values tell me, in this case, one of them is a hole and one of them is a vertical asymptote. They could both be holes or they could both be vertical asymptotes, but that's what we're trying to figure out. So take a moment to go through each step. I'll leave this up here on the screen so that you can copy it down. But also I want you to try to just go from step to step. So you're gonna go from the equation, right, to the factored form. From the factored form, you're gonna look for the thing that cancels. In this next case, nothing cancels. So we're just gonna write none here. And then that means that there are two things in the denominator to end up over here. So we have those two answers there. When we get those two answers, that means we have two vertical asymptotes. And you can see how that changes the graph over here. We have one vertical asymptote right here and one right here. And you can see that because of those asymptotes, the line actually creates this three-part version there. So take a moment. I'll leave this on the screen for you and go slowly through each one. But this is that next one. You can pause the screen if you need it. This is that one after that. And go ahead and take a moment to fill in this section here, that last section. Pause the video to work on this if you need to. So then finally, the last thing that I want us to notice is today's big idea, right? So today's big idea, there are two of them. If a factor in the denominator cancels, it becomes a hole in the graph, right? So if we look back at the three examples that are done here, if we look at these ones that cancel in this section here, we can see that there is a hole at -6, and we see that hole on the graph. We see a hole at -1, and we see that hole on the graph, right? So these are the places where the factors cancel. So when things cancel out like this or like that, that becomes our hole. So that's our first big idea here. First big idea. Our second big idea is if a factor in the denominator doesn't cancel, it becomes a vertical asymptote, right? So we can see in this last section, something that doesn't cancel, like this x plus 0, right? We see that x plus 0 here. Here we had that -5 and +2. We saw -5 and +2. And then here in this one, the one that doesn't cancel is x equals 1. And we see that vertical asymptote there, right? So if it cancels, it becomes a hole. If it doesn't cancel, it becomes a vertical asymptote. And that is our big idea for today. Thanks, y'all.